In the last lecture, we examined the basics of energy efficiency: a well-insulated, airtight building envelope, energy-efficient windows and doors, and energy-efficient HVAC systems and appliances. Now, whenever I speak on this subject, the first question I invariably receive is, how much can I really save by implementing these measures in my own home? Well, it depends. It depends on how much you're willing to spend. For example, foamed-in-place urethane insulation costs considerably more than fiberglass batting, but it also provides twice the thermal resistance. It depends whether you're building a new home or rehabbing an old one. In general, energy efficiency measures are less expensive and more effective in new construction. And it depends on how you implement these measures. You'll realize a far better return on your energy efficiency investment if you implement the basic energy efficiency measures comprehensively rather than piecemeal. It makes little sense to invest tens of thousands of dollars in high-performance windows or radiant floor heating only to lose most of your heat through leaky, poorly insulated walls. I'll add that the potential energy savings for your home can be determined with a fairly high degree of accuracy. If you're designing a new home, an expert in building science can use computer software to model your building envelope and calculate your expected energy use for various design alternatives. This will help you identify the trade-offs between upfront cost and long-term benefits for each alternative. And then you can pick the one that works best for you. If you're planning an energy retrofit of an existing home, you can call in an energy auditor to test your building envelope and HVAC system, and then guide you toward a rehab scheme that will meet your goals. So, how much can you save? Well, recognizing that it depends isn't really a particularly satisfying answer, I'll try to provide something more definitive at the end of this lecture. Now, effective as they might be, the basics of energy efficiency are really just incremental improvements over the old ways of reducing consumption. More insulation, better control of air infiltration, better windows, more efficient appliances. But in this lecture, we're going to break with the past as we look at a fundamentally new paradigm called passive solar design, a more holistic approach that considers energy efficiency in many of the most fundamental decisions about a home's design. The concept of passive solar design derives from a recognition that energy efficiency can be enhanced not only by reducing consumption, but also by tapping into an abundant and readily available supply of free energy, the thermal radiation of the sun. In passive solar design, a building's location, orientation, architectural configuration, and interior features are chosen first and foremost to maximize solar heat gain in the winter and to minimize it in the summer. This approach is characterized as passive because it employs no mechanical or electrical devices to harvest solar energy. A passive solar house merely uses the sunshine that falls upon it in a variety of ingenious ways. Now, we use many forms of solar energy, often without even realizing it. There's photovoltaic power generation, of course, but in a broader sense, most other forms of power generation also depend on solar energy at the most fundamental level. Fossil fuels originated as plants and microorganisms that acquired their biomass through photosynthesis. Hydroelectric power is dependent upon the hydrologic cycle, which is powered by the sun. And the wind that drives our wind turbines is caused by differences in atmospheric pressure resulting from solar heating of the Earth. What makes passive solar unique is that it uses solar energy directly and therefore more efficiently. To illustrate this point, consider the heat produced by the electric heat pump in my home. It starts out as coal, which is extracted from the earth, processed, transported to a power plant, and burned to produce steam for power generation. The resulting electrical power is then transformed, transmitted, transformed again, and distributed to my house, where it's used to drive the heat pump's compressor and blower, causing warm air to emerge from the supply duct in my living room. At every stage of this sequence of processes, some energy is consumed and quite a lot more is lost to the inherent inefficiencies in converting from one form of energy to another. Consequently, the amount of heat actually transferred into my home by the heat pump is actually only about 15% of the chemical energy that was originally available in the coal. In contrast, a passive solar home cuts out all the middlemen. The sun's thermal radiation enters the house through windows, it impinges directly upon floors, walls, and furniture, and about 70% of it is re-radiated back into the room as heat. And 100% of this heat is free. Your dog instinctively understands this process, which is called direct solar heat gain, or simply direct gain. And the single most important principle of passive solar design is that the house should be oriented to maximize direct gain. Now, in the Northern Hemisphere, the building should have one wall facing as closely as possible to the south, such that it receives maximum possible exposure to the sun. The long axis of the building should be oriented east to west, so that the southern wall is longer than the eastern or western walls. And there should be no trees, neighboring buildings, or terrain features that prevent winter sunlight from reaching this southern wall. By the way, through the remainder of this discussion, I'll assume that we're talking about a house in the Northern Hemisphere. If you happen to be living in the Southern Hemisphere, every time I say south, translate that as north and vice versa. Now, to make the best use of direct gain, you've got to hold on to it. So the passive solar home must be extremely well insulated and airtight. Note that passive solar design doesn't reject the basic methods of achieving energy efficiency. It actually demands that these methods be implemented to a very high standard. For example, the National Renewable Energy Laboratory advocates the 30-40-50 standard, meaning R30 insulation for floors, R40 for walls, and R50 for roofs. That's a tall order, considerably more than the current building codes require. And that's why passive solar homes are often built with structural insulated panels, or SIPs, like this one, or unconventional framing methods that can accommodate thicker insulation while minimizing thermal bridging. With this much thermal resistance, a little bit of solar gain goes a long way. Now, the passive solar home is also meticulously sealed to prevent air leaks, and then tested with a blower door or with this tool, the thermal imaging camera, which is used to identify and document spots where the thermal performance of the building envelope is inadequate. And as we've seen, an airtight building envelope demands that a heat recovery ventilator be used to keep the inside air fresh without incurring major heat losses. In passive solar design, no component of the building receives more attention than the windows, and with good reason. Windows are essential for achieving heat gain, yet they're also the greatest source of heat losses. Thus, determining the required window area in a passive solar home is a delicate balancing act. Too small, and direct gain in the winter will be inadequate. Too large, and the house will overheat in the summer and lose too much heat in the winter. Now, in heating climates, that is, in colder regions where heating demands exceed air conditioning demands, south-facing windows should be relatively large and numerous. Their actual size is typically calculated as a percentage of the floor area, with a percentage determined by the climate and latitude. The north, east, and west-facing walls should have only enough window area to provide adequate natural lighting. To minimize heat losses, all windows should have the lowest possible U factor. But to properly control direct gain, the solar heat gain coefficient should be high for south-facing windows and low for all the others. In cooling climates, where air conditioning demands exceed heating demands, north-facing windows should be larger and should be the preferential source of interior lighting. South-facing windows should be smaller and shaded with roof overhangs or awnings to prevent direct gain in the summer. And all windows should be rated for both low solar heat gain and low thermal transmittance. In heating climates, direct gain through south-facing windows is often controlled with a carefully proportioned roof overhang, which shades these windows in the summer when the midday sun is high in the sky, but doesn't in the winter when the sun is lower. Now, to see how the overhang works, let's design one. Suppose we're planning to build a passive solar house right here in Chantilly, Virginia, home of the great courses. Before we can configure the overhang, we need to determine the maximum and minimum angles of the sun above the horizon at midday over the course of a year. These two extremes occur on the summer and winter solstices, respectively, and the angles depend on the latitude at the location of interest, which in this case is, right here, 39 degrees north latitude for Chantilly. Now, on the summer solstice, the Earth's axis is tilted directly toward the sun, and I'll use this yellow ball to represent the sun. And the sun's angle above the horizon at midday can actually be calculated as 90 degrees minus the latitude plus the angle at which the Earth's axis is tilted. That's 23.5 degrees. And the result is 74.5 degrees. On the other hand, on the winter solstice, the Earth's axis is tilted the other way, directly away from the sun. And the sun's angle on this day is 90 degrees minus the latitude minus 23.5 degrees, or 27.5 degrees. Now let's plot these results on a scale drawing with a 36-inch tall window. The summer solstice line extends up from the bottom of the window at 74.5 degrees, and the winter solstice line extends from the top at 27.5 degrees. These lines intersect at the point where the outer edge of the overhang should be. And by measuring this scale drawing, we can determine that the overhang should be 6 inches up from the top of the window and 11 3/4 inches out from the face of the wall. With this overhang in place, our 3-foot window will be fully shaded at noon on the summer solstice, and it will receive a full dose of solar gain on the winter solstice. Now, if you don't want an overhang, perhaps for aesthetic reasons, you can achieve a similar effect through careful placement of deciduous trees on the south side of the house. In winter, deciduous trees allow more than 60% of the sun's direct thermal radiation to pass through them, and in summer, they block nearly all of it. While we're on the subject of trees, it's also beneficial to have evergreen trees on the north, east, and west sides of the house, both to shelter the building from cold winds and to prevent unwanted solar gain through east and west-facing windows in the morning and evening. But wait, why would we want to prevent solar gain from the east and west in a heating climate? Well, the answer is that solar gain from these directions can't be controlled seasonally with overhangs because the sun's path is low in the eastern and western skies throughout the year. Thus, uncontrolled solar gain through these windows is likely to cause overheating in the summer, no matter what we do. For this same reason, skylights can be problematic in passive solar design. Because of their orientation, they tend to allow maximum direct gain in the summer, precisely when we don't want it, and relatively little in the winter, because the low angle of the sun causes most of the thermal radiation to be reflected rather than transmitted. Well, at this point, you're probably asking, what happens at night when there's no solar gain to heat the house? Well, good question. In heating climates, passive solar homes incorporate properly configured thermal mass to mitigate against fluctuations in outside temperature over the course of a 24-hour day. Thermal mass is, in essence, an object's capacity to store heat. Common materials with high thermal mass include concrete, tile, stone, soil, and water. The concept is to place, say, an exposed concrete floor or a stone wall within interior spaces adjacent to south-facing windows. Solar energy falling upon these surfaces is absorbed during the day and then re-radiated slowly back into the home throughout the night. Thermal mass can also be used as an air conditioner, as long as it's positioned such that it doesn't receive direct gain from the summer sun. As cool night air circulates across this mass, heat is transferred from the mass to the air. And then during the day, the mass absorbs heat from the warmer inside air, cooling the house. A closely related passive solar technique is called earth sheltering, embedding the home's northern wall, at least in part, within a hillside like this. And what we see is that here, the soil serves as a thermal mass, which helps to reduce daily fluctuations in indoor air temperature year-round. Earth sheltering also adds thermal resistance to the building envelope and shelters it from those cold north winds. As we've seen, in passive solar design, the collection and storage of solar energy is usually quite localized. It all happens in the immediate vicinity of those south-facing windows. A significant challenge, then, is distributing this heat more or less evenly throughout the occupied space. This can be done with mechanical ventilation, but fans consume electrical power that we're trying to save, so it's really preferable to use natural means to the greatest extent possible. To this end, the most successful passive solar homes typically use a relatively small footprint and an open interior plan to promote natural air circulation. In warm weather, natural cooling can be enhanced by positioning windows to achieve cross-ventilation and by using upper-level openings to exhaust naturally rising hot air. This latter phenomenon, called stack ventilation, is often promoted by incorporating a tower or split roof, like this one, into the architectural design. When vents or windows on the highest level are open, hot air is constantly being flushed out and cooler air is drawn in from below, preferably through vents located on the shadiest side of the house, perhaps a porch or a shaded garden. Although the focus of passive solar design is on heating and cooling, a variety of other energy-saving measures are often incorporated into passive homes. These include using solar hot water heaters, solar cookers, harvesting heat from wastewater, purposeful use of refrigerators, computers, and other electronic devices as heat sources, and perhaps most importantly, maximizing natural illumination. Now, as we saw in our last lecture, electric lighting accounts for about 6% of power consumption in the average US residence. That's not a huge number, but every little bit helps. And that 6% can be drastically reduced with purposeful design for natural lighting. And wherever supplemental artificial lighting is still needed, by switching from those power-hungry incandescent bulbs to highly efficient light-emitting diode or LED bulbs. As we've seen, the size, placement, and types of windows used in a passive solar house should be based first and foremost on facilitating or preventing direct solar gain, and second, on preventing heat loss. Given these constraints, it's generally not going to be possible to tailor the window configurations for optimized natural lighting. Rather, we need to look beyond the windows to the placement of individual rooms within the architectural floor plan. Now here, the concept is to consider the time of day when each interior space will be used most intensively, and then to position that space where the natural light will be optimal at that same time. For example, the kitchen might be placed in the southeast corner of the floor plan because it's used most intensively in the morning, and the living room in the southwest corner to facilitate its use in the late afternoon and evening. Bedrooms would logically be placed on the northern side because they usually aren't used during the day. The master bedroom might be on the northwest corner to take advantage of late-day sun and to avoid early morning glare. But there are no universal answers here. The design can and should reflect the occupant's individual lifestyle and preferences. And that leads to two broader observations about passive solar design. First, this approach is truly holistic. No aspect of a passive solar design, not even the layout of rooms on a floor plan, is exempt from being reinvented for the sake of improved building performance. And second, when it's implemented well, The passive solar approach leads to individualized designs that are uniquely suited to their location, climate, and occupants' needs. What an incredibly refreshing change this is. In the vast majority of modern residential developments, there are perhaps 4 or 5 standard floor plans arrayed around cul-de-sacs at every possible orientation without regard to how people will actually live their lives within. Passive solar design rejects these sorts of standardized one-size-fits-all solutions. And in doing so, this approach is actually returning us to our historical roots. For most of human history, residential buildings have been thoughtfully adapted to their latitude, local climate, and intended use. The great Roman engineer Vitruvius, writing in the 1st century BC, described this design philosophy quite effectively, as he specified, for example, that the north-facing walls of buildings should be thicker than the south-facing walls for improved insulation. Ancient Roman bath complexes typically had their heated rooms located on a south-facing wall. This Native American pueblo incorporates natural shading and thoughtfully controlled window sizes. Many of these classic New England salt box houses were oriented with the front 2-story wall facing south and the single-story back wall facing north. This is highly competent passive solar design, even if the designers wouldn't have known it as such. Indeed, it wasn't until relatively recently that the availability of safe, effective technologies for artificial heating and cooling, combined with a seemingly limitless supply of cheap energy, led to the current penchant for mass-produced look-alike houses, designed with little or no regard for geographic context. Today, it's hard to tell if a residential development like this one is in Minnesota or in Mississippi, and that just doesn't make a lot of sense. In contrast, consider this passive solar home, recently built by my good friend Fred, a West Point faculty colleague. Here we see all of the essential passive solar design features: large south-facing windows, appropriately sized overhangs, reduced glazing on the east and west walls, a tower to promote stack ventilation, thoughtful adaptation to the site. It's built with structural insulated panels, heated quite effectively with a tiny energy-efficient furnace, and ventilated with an HRV. Oh, and by the way, it's both beautiful and architecturally distinctive. This distinctiveness is a benefit of passive solar design that's seldom articulated, but is, I believe, quite compelling. So, how effective is this approach at achieving its primary purpose of reduced energy consumption? Well, once again, the answer is, it depends. It depends on climate. For example, heating climates with relatively large diurnal temperature fluctuations are more likely to yield dramatic results than warm, humid climates. More importantly, it depends on the extent to which passive solar principles are actually implemented. One study suggests that for a modest implementation of these principles, 5 to 25% of a home's required heating load can typically be met by solar gain. But for more rigorous implementation, that number can easily exceed 75%. And in a moderate climate, with rigorous implementation and high-quality construction, it's quite possible for a passive solar home to require no mechanical heating or air conditioning at all. Even in such cases, however, a small supplemental heating appliance is usually included in the design for unexpectedly cold weather or for emergencies. This might be an electrical resistance baseboard heater, for example, which would be quite energy inefficient if it were used for extended periods. But it's a reasonably effective and highly responsive way to provide localized heating for short periods of time. An increasingly popular alternative is the ductless mini-split, a small heat pump with an exterior unit more or less like that of any other air source heat pump, but an interior unit that mounts directly on a wall and blows hot or cold air directly into the conditioned space with no ducts. Elimination of ductwork significantly reduces heat losses and thus contributes significantly to this system's impressive energy efficiency. On the other hand, the ductless mini-split generally works well only for heating individual rooms or for smaller homes with open floor plans, which allow for better circulation of hot and cold air from this single source. Well, just as the effectiveness of passive solar design depends on the extent and quality of implementation, so does its cost. Certainly, super windows and R40 wall insulation could add significantly to the construction cost. But with the possibility of heating load reductions exceeding 75%, it's literally only a matter of time before energy cost savings fully offset the additional construction costs. It's also important to recognize that many of the most essential features of passive solar design can be implemented at zero additional cost. The house's orientation costs nothing. Getting the floor plan right for optimized natural lighting costs nothing. The concrete floor slab you'll be using for thermal mass had to be there anyway. Well, if you think, as I do, that passive solar design is an incredibly intriguing concept, well, you ain't seen nothing yet. Today, we're seeing an increasing number of homeowners and builders taking another big step forward with the net zero energy home, a building that requires no net input of energy over the course of an entire year. Now, most net zero homes aren't actually self-sufficient on a day-to-day basis. Rather, they produce as much energy as they use on an annual basis. To achieve this outcome, they typically combine aggressive implementation of passive solar design principles with one or more active in-home renewable energy sources, such as photovoltaics, a wind turbine, or geothermal power generation. These homes inevitably draw some electrical power from the grid when demand is unusually high, in extremely cold or hot weather, for example, or when on-site power generation is low, for example, when the sun isn't shining or the wind isn't blowing. But then they return an equal amount to the grid during periods when they're generating more energy than they consume. So, earlier in the lecture, I posed the frequently asked question, how much energy can I really save? Net zero design provides us, finally, with an unambiguous answer. We can save all of it. I should note that net zero design only makes sense if the electric utility offers net metering, the practice of giving credit at the retail price for consumer-generated power that's supplied to the grid. This is currently not an issue in the US since the Energy Policy Act of 2005 required all public utilities to offer net metering to their customers. Another important example of the healthy role that government policy can play in promoting technological development. It's hard to imagine many of the recent advances we've seen in residential energy efficiency and small-scale renewable power generation without the incentive provided by net metering. So what's the value of passive solar design, net zero design, and green building in general? Well, obviously, these initiatives are delivering on their promise, saving energy for homeowners, helping reduce pressure on electric utilities to increase generating capacity to meet peak demands, and measurably reducing the adverse impact of residential construction on our environment. But there are important benefits beyond these obvious ones. First, these new approaches are fundamentally changing the way we think about our homes. Thanks to passive solar design, we can once again think of a home not as a one-size-fits-all commodity, but as a uniquely crafted system that reflects both the region in which it's built and the people who reside within. Thanks to passive solar design, we could also think of a home as a very different sort of investment than we have in the past. It's no longer necessary to invest in a home purchase in the hope that it'll gain value over time. We can now invest in energy efficiency, confident that it will pay off in reduced energy costs over time. Nonetheless, every investment entails risk, and it's certainly true that over the years, some new residential construction technologies have been billed as revolutionary, but subsequently proved to be colossal failures. For example, back in the 1970s, aluminum electrical wiring was all the rage, until it was implicated in a series of catastrophic fires. During that same period, a product called urea formaldehyde foam was used extensively for insulation in residential construction, A decade later, it was found to cause serious health problems. If these sorts of horror stories make you uneasy about the new green building technologies, well, so be it. But we should all recognize and be thankful that right now, early adopters of passive solar design, like my friend Fred, are effectively assuming this risk on our behalf, proofing new concepts and technologies, generating the data that will help differentiate between the good ideas and the bad, and ultimately advancing the state of the art in ways that will benefit all of us. Reaping these benefits isn't easy. Doing passive solar design well requires a design professional with expertise in building science. It requires sophisticated computer modeling to analyze and compare design alternatives and to determine heating and cooling loads. It requires a thoughtful, holistic, context-specific planning process that integrates passive solar principles into every aspect of design, construction, and in-progress testing. And it requires the integrated effort of a project team that's committed to getting the details right. In this sense, green building is actually pushing the entire construction industry in healthy directions that it probably wouldn't have gone otherwise, toward better science, more holistic design, and better construction integration. In short, toward a higher level of professionalism. Whether we embrace green building or not, we'll all benefit from this trend. Next lecture, we'll begin studying the last of your home's 8 engineered subsystems, the telecommunications system. In this lecture, we'll explore an everyday technology that very few of us have ever actually seen or will ever see, the satellite. Now, in one sense, no other technology we've discussed in this course is quite as remote from our day-to-day experience. Satellites are literally out of this world, orbiting hundreds or even thousands of miles above the Earth's surface. Yet, I don't think I'll have any problem convincing you that satellite technology belongs in this course on everyday engineering. Satellites directly influence our daily lives when we check tomorrow's weather forecast, watch satellite TV, listen to satellite radio, watch a live TV news feed transmitted from a remote location halfway across the globe, or use a GPS device for navigation. There are 7 major types of satellites. Communication satellites facilitate global telecommunications in a wide variety of forms: television, radio, internet, telephone, and specialized business transactions. Navigation satellites are used to determine locations on the Earth's surface or in the air by transmitting radio signals to mobile receivers. Reconnaissance satellites are used for military and intelligence purposes, including high-resolution photography, communications interception, covert communications, monitoring nuclear test ban compliance, and detection of missile launches. Earth observation satellites perform non-military observation functions, such as environmental monitoring, meteorology, and map-making. This category includes National Weather Service satellites used for weather monitoring and forecasting. Astronomical satellites are used for observing distant planets, galaxies, and other heavenly bodies. The Hubble Space Telescope is a good example from this category. Scientific satellites are used to perform scientific experiments in such fields as biology, chemistry, metallurgy, botany, and medicine. Finally, a space station is a satellite that's inhabited by humans. The International Space Station is the most recent example of this technology. There are currently over 1,000 operational satellites in Earth orbit, owned all or in part by over 100 different countries. These represent a diverse mix of all 7 types. Some are military, some governmental, some commercial. In this lecture, we'll look at 2 types of satellites that have the greatest direct impact on our everyday lives: communications and navigation. But first, we'll need to review a few basic concepts in the science of orbital mechanics. Yes, this is rocket science. Modern orbital mechanics has its roots in Kepler's laws of planetary motion, first published by Johannes Kepler in 1609, and in the more general laws of universal gravitation and celestial motion, published by Sir Isaac Newton in his monumental work, Mathematical Principles of Natural Philosophy, in 1687. For the purpose of today's lecture, there are 5 key concepts in orbital mechanics that we need to understand. 1. A satellite's orbit is elliptical, with the planet located at one focus of the ellipse. 2. On an elliptical orbit, the closest point to the planet is called the perigee, and the farthest point is the apogee. 3. A line drawn from the planet to the satellite sweeps out an equal area in an equal period of time at any location in the orbit. Thus, the satellite moves faster when it's closer to the planet and slower when it's farther away. 4. Once a satellite is in orbit, the orbit's characteristic shape and orbital period won't change unless the satellite is subjected to an applied force, such as thrust from a rocket engine or drag caused by interaction with the atmosphere. And 5. As the two foci of an elliptical orbit get closer together, the shape of the orbit becomes progressively closer to a circle. Mathematically speaking, the ellipse becomes progressively less eccentric. Thus, a circular orbit is really just a special case of an elliptical orbit, one for which the two foci correspond. For a circular orbit, the altitude of the satellite, that is, the distance from the Earth's surface, never changes. Thus, its speed must be constant. And according to Kepler's laws, both the speed and orbital period for a body orbiting the Earth can be calculated using these 2 equations, where r is the radius of the orbit, and the Greek letter mu is a number called the standard gravitational parameter, which, if you're interested, is actually equal to Isaac Newton's universal gravitational constant times the mass of the planet. What's really important here is that the speed and period of a circular orbit depend only on its radius, not on the mass of the satellite. To illustrate the use of these equations, let's consider a satellite in a circular orbit with an altitude of 100 miles. Now, the radius of this orbit is its altitude, 100 miles, plus the radius of the Earth, 3,960 miles. Substituting, we find that the satellite orbits the Earth in under 1.5 hours, and it moves at over 17,000 miles per hour. Earth orbits are generally classified in 4 categories. A low Earth orbit, or LEO, is a circular orbit with an altitude between 100 and 1,240 miles above the Earth's surface. Note that the example we just worked is a low Earth orbit. The medium Earth orbit is a circular orbit with an altitude between 1,240 and 22,236 miles. At the precise altitude of 22,236 miles is the geostationary orbit, or GEO. We'll return to this very special orbit in just a moment. And finally, the elliptical orbit is used to transfer a satellite from one circular orbit to another, as we'll see shortly, and for other special purposes. Now let's see why the geostationary orbit is so special. Using our orbital mechanics equation, the orbital period of a geostationary orbit works out to be 23.93 hours, which is exactly equal to 1 sidereal day. A sidereal day is the time it takes for the Earth to complete one full rotation with respect to a non-rotating frame of reference. Watch. On this diagram, the Sun is directly overhead at this particular location on the Earth's surface at time 1. Now, at time 2, the Earth has rotated through exactly 360 degrees. But because it's also revolved 1/365th of the way around the Sun during the same period, the Earth must now rotate just a bit more before the Sun is directly overhead once again. The period of time from 1 to 2 is a sidereal day of 23.93 hours, and from 1 to 3 is our standard solar day of 24 hours. Because a geosatellite's orbital period exactly matches the Earth's rotational period, the satellite remains perfectly stationary at one point in the sky from the perspective of an observer on the Earth's surface. That's why we can aim our satellite dishes at one point in the sky and never have to adjust them. That's why most communication satellites use geostationary orbits. By the way, the concept of using geostationary orbits for satellite communication is attributed to none other than Arthur C. Clarke, the science fiction writer I quoted in our first lecture. Perhaps truth really is stranger than fiction. Now, it's important to recognize that there is only one geostationary orbit, 22,236 miles above the equator, and there are currently about 400 satellites in it. If these satellites were uniformly spaced around the circumference of the orbit, the distance between them would be more than adequate, over 400 miles. However, they're not uniformly spaced because a communication satellite needs to be more or less centered over its coverage area to do its job. Thus, geosatellites are concentrated most densely over the most technologically developed regions of the world. In these regions, it's not unusual for geosatellites to be separated by fewer than 5 miles. Given that they're moving at almost 7,000 miles per hour, this really isn't a lot of space. To minimize the possibility of collisions and electronic interference, each satellite is assigned an orbital station, which is really just a longitude, by the International Telecommunication Union. And as you might guess, a station in a geostationary orbit is one of the world's most prized pieces of real estate. But how does a satellite actually get inserted into its assigned orbital station? Well, to answer that question, let's follow the launch, deployment, and employment of a typical geostationary communications satellite. Along the way, I hope you'll come to appreciate the extraordinary sophistication in the design and production of these systems. Now, since the shutdown of the US Space Shuttle program in 2011, all satellites are boosted into orbit by expendable launch vehicles. A variety of different commercially available rockets are used for this purpose. For our hypothetical mission, we'll use a typical example, an Atlas V rocket launched from Cape Canaveral, Florida. The Atlas V is a two-stage expendable launch vehicle built by the United Launch Alliance, a joint venture of Lockheed Martin and Boeing corporations. The Atlas V weighs over 700,000 pounds at launch, and it's capable of lifting a 64,000-pound payload into low Earth orbit or a 28,000-pound payload into geostationary orbit. Note that geosatellites must be considerably lighter than LEO satellites because the geostationary orbit is so much higher. At the most fundamental level, a rocket engine is a simple application of Newton's third law. For every action, there is an equal and opposite reaction. Combustion of fuel causes high-pressure exhaust gases to be expelled at high speed from the engine's combustion chamber through a nozzle, which further accelerates the gases to supersonic speed. In the context of Newton's third law, the action is the rearward acceleration of the exhaust gas's mass, and the equal and opposite reaction is forward thrust, a force that causes the rocket to accelerate. A two-stage vehicle like the Atlas V is really two rockets, each with its own engine and fuel supply, stacked one on top of the other. When the first stage runs out of fuel, it's jettisoned, thus reducing the overall weight of the system and allowing the smaller second stage engine to accelerate the lighter vehicle to its final altitude and speed. Now, prior to launch, our satellite is folded up and stowed within a shroud at the top of the launch vehicle, as shown here. At launch, the Atlas V's first stage engine burns for about 4 minutes. The first stage is then jettisoned and it falls into the ocean. That's why it's called an expendable launch vehicle. The second stage takes over immediately, powering the payload into a circular, low Earth parking orbit, and then it shuts down. The shroud is jettisoned, and then the second stage engine is restarted to initiate an elliptical transfer orbit that will take the payload to geostationary altitude. To understand how this works, let's look at 3 relevant orbits. Let's say that the low Earth parking orbit has an altitude of 100 miles. We've already calculated the corresponding speed of this orbit at 17,500 miles per hour. In the desired geostationary orbit, the satellite will have an altitude of 22,236 miles and a speed of 6,877 miles per hour. To transfer from the parking orbit to the geostationary orbit, we need to design an elliptical orbit with its perigee at 100 miles and its apogee at 22,236 miles. Based on Kepler's laws, the speeds associated with this elliptical orbit can be calculated as 22,670 miles per hour at perigee and 3,600 miles per hour at apogee. Therefore, to transfer from LEO to GEO, we first execute a second stage engine burn that increases the rocket's speed from 17,500 to 22,670 miles per hour. This places the craft on the desired elliptical transfer orbit. The second stage would typically be jettisoned at this time. Now, because the satellite is now in an elliptical orbit, it slows down as it gets farther away from the Earth, reaching its minimum speed of 3,600 miles per hour at the apogee. At precisely this moment, the satellite must fire its primary rocket thruster to increase its speed to 6,877 miles per hour, at which point the vehicle assumes a circular orbit at geostationary altitude. So we've now got the speed and the altitude right, but this isn't a true geostationary orbit yet, because we launched from Cape Canaveral, located at 28.5 degrees north latitude. Our current orbit is inclined at 28.5 degrees to the equator. To achieve a true geostationary orbit, our transfer maneuver must also include a directional change that reorients the orbit into the plane of the equator. But merely achieving the geostationary orbit isn't good enough. We must achieve it at precisely the correct orbital station as assigned by the International Telecommunication Union. Doing so requires perfect timing of the engine burn that initiates the transfer. Now, commanded by a ground-based control center, the satellite now orients itself, deploys its antennas and solar arrays, senses the position of the Earth and Sun, establishes communication links, and becomes operational. The satellite is composed of two major components, the mission payload and the support platform, also called the bus. The bus is responsible for transporting the mission payload into orbit. It provides electrical power, attitude control, temperature control, and orbital adjustments. The satellite's attitude, that is, its orientation in space, is controlled with respect to a reference axis system that was actually borrowed from the world of aeronautics. The three axes of rotation are called pitch, yaw, and roll. The pitch axis is parallel to the Earth's axis. That is, a rotation about the pitch axis looks like this. The yaw axis is pointed from the satellite directly at the center of the Earth. So rotation about the yaw axis looks like this. And the roll axis is tangential to the orbit. So rotation about the roll axis looks like this. Now, the typical communication satellite has two large solar arrays, which serve as the sole source of electrical power in orbit. They're also used to charge batteries, which supply power when the satellite passes through the Earth's shadow. The arrays are oriented along the pitch axis, as you can see here, and they must rotate continuously on this axis, following the Sun as the satellite orbits the Earth. To see how this process works, let's assume that you are the Sun. And so with the satellite in this position, the arrays must be positioned like this, so that they're oriented toward the Sun. Now, as the satellite orbits, the communications antennas must remain pointed at their designated coverage areas on the Earth's surface, called the footprint. And so, as the satellite orbits, the arrays must rotate continuously like this, even as the satellite continues to point toward the Earth. To control the satellite's position and attitude, the bus uses two separate systems, rocket thrusters and reaction wheels. This array of rockets typically includes one primary orbit maneuver thruster and 12 attitude and orbit control thrusters, arranged such that the bus can be propelled or rotated in any direction with great precision. These thrusters are used for the final insertion into geostationary orbit, for the initial orientation of the satellite, and for station keeping, the process of adjusting the orbit to keep the satellite at its prescribed altitude and longitude. Station keeping is required to correct naturally occurring perturbations in the orbit caused by the gravitational attractions of the Sun and Moon and by variations in the Earth's own gravitational field. Thrusters are generally not used for attitude control because they're powered by propellant, and when the propellant supply is used up, the satellite becomes useless. Today, there are many satellites in orbit that are fully functional but inoperable simply because they ran out of fuel. Rather than using thrusters, the bus controls the satellite's attitude with reaction wheels. Now let's imagine that this box is a satellite bus in orbit around the Earth. Of course, an actual satellite would be free to rotate about all of its three axes, pitch, roll, and yaw. But for simplicity, my model is only more or less free to rotate about its pitch axis, like this. And up above here is a reaction wheel, which is powered by an electric motor located inside the satellite bus. Now suppose we need to reorient the satellite about its pitch axis. I'll do this by increasing the motor's rotational speed. Sir Isaac Newton tells us that the resulting action, rotational acceleration of the wheel, will cause an equal and opposite reaction, rotational acceleration of the bus in the opposite direction. Watch. Notice how just a slight increase in the speed of the rotating wheel causes the bus to rotate as well. Now, my model has enough friction to stop that rotation of the bus eventually. But in the actual system, we'd have to decelerate the reaction wheel at the appropriate point to stop the bus's rotation at the desired attitude. So now, watch what happens when I decrease the speed of the reaction wheel. Notice that simply decelerating the reaction wheel now caused the satellite bus to accelerate in the opposite direction. And it's through this mechanism that the attitude of the satellite about its pitch axis can be very precisely controlled. My model has one reaction wheel, but a typical satellite has four, located as close to the satellite's center of mass as possible, and arranged with one each on the pitch, roll, and yaw axes, and one oriented on a diagonal to serve as a backup if any of the primary wheels should fail. Sensors continuously monitor the satellite's attitude, and controllers make minute adjustments to the wheel's speeds to keep all three axes oriented properly. Most important, because the reaction wheels are driven by electric motors, they use electricity generated by the solar arrays, and they don't deplete the satellite's precious supply of rocket propellant. The bus also includes a telemetry system that continuously transmits information about the satellite's status, attitude, power production, propellant supply, temperature, and so forth to a command and control station on the ground. So finally we come to the mission payload, the satellite's communications package. The basic function of a communication satellite is to receive radio signals called uplinks from a ground-based transmitter, amplify these signals, shift their frequency, and then retransmit them as downlinks to the Earth's surface. High-frequency radio waves propagate in straight lines. They can't bend around the curvature of the Earth. Thus, satellites facilitate the transmission of radio signals over long distances without having to use a string of terrestrial relay stations, as is the case with conventional microwave communications. The shift in frequency is needed to prevent interference between the uplink and the downlink. By the time the uplink reaches the satellite's altitude, its strength is quite weak. If it weren't for the frequency shift, the high-powered downlink would overwhelm the uplink. Communication services handled by satellites include TV, radio, internet, telephone, and some specialized business communications. Satellite telephone service is generally much more expensive than the use of landlines, cell phones, and undersea cables, particularly now with the advent of fiber optics. So satellite phones are used primarily in remote areas that don't have other phone services available. Because the geostationary orbit is so high, there's a substantial delay in radio transmissions to and from the satellite, about 1/4 second each way, even though these transmissions travel at the speed of light. This delay can cause problems for two-way communications and certain types of data transmission, for example, internet gaming. But it poses no problems for one-way broadcasts like radio and TV, hence the growing popularity of these services. The mission payload consists of two main elements: antennas and a repeater. Most communication satellites are equipped with at least two dish antennas. These may be used for communications on two different frequency bands, or they may be aimed at two different footprints on the ground. But each antenna is generally used for both receiving and transmitting. Because radio signals are so weak by the time they reach the altitude of a geosynchronous orbit, these antennas must be as large as possible. Nonetheless, they're normally limited to a diameter of about 7 to 10 feet so they can fit inside the launch vehicle's protective shroud. As this diagram shows, the repeater includes a radio receiver, which receives the uplink and feeds it to an array of parallel transponders, each corresponding to a particular service: TV, voice, internet, radio, and a particular frequency band. Most repeaters have 24 or more transponders. Each contains an input filter, which separates out the particular signal that's assigned to that service, an amplifier, which boosts the strength of the uplink signal by as much as 10 million times, and an output filter, which performs the frequency shift required to prevent the uplink and the downlink from interfering with each other. And by the way, these amplifiers invariably use old-fashioned vacuum tubes rather than transistors, because tubes are generally more effective in high-powered, high-frequency applications. This system communicates with a worldwide network of ground-based telecommunications ports, or teleports, which exist to provide customers with access to satellites. Equipped with antennas, transmitters, receivers, and routing equipment, the teleport receives signals from a variety of sources, like the public switch telephone network, the internet, and cable TV networks, and sends these signals as uplinks to the appropriate satellites. Similarly, the teleport receives satellite downlinks that originated elsewhere and routes them to the appropriate destination. But not all downlinks pass through the teleport. Over the past few decades, development of high-frequency, high-powered satellite transmission capability has stimulated the development of the Direct Broadcast Satellite Service, which produces broadcast signals capable of being received by the small dish antennas that have now become so popular with consumers. This capability, more than any other, is driving the continued economic viability of satellite communications. It's important to recognize that geostationary satellites aren't the only type of communication satellite. A relatively recent alternative is to use a constellation of LEO satellites, which are less expensive to launch, require less power for signal transmission, and are much less susceptible to the transmission delays associated with geosatellites. However, these systems require far more satellites to provide adequate coverage of the Earth's surface. A typical example, called the Iridium system, uses 66 of them. And because LEO satellites move at such high speeds, transmissions are constantly being handed off from one satellite to the next, in much the same way that cellular systems hand off calls from one cell to the next. In recent years, one of the greatest impacts of satellite technology on our everyday lives has been the advent of highly accurate satellite-based navigation through the Global Positioning System. The GPS was developed in the early 1970s by the U.S. Department of Defense for military use. But in 1983, President Ronald Reagan directed that the technology be made freely available for civilian use as well. Today, the system continues to be owned and operated by the U.S. government as a national resource, and the DoD is charged with operating and maintaining satellites ground antennas, and control stations. GPS uses a constellation of 32 satellites in medium Earth orbit, flying at an altitude of 12,600 miles with a corresponding orbital period of 12 hours. These satellites move in multiple orbital planes such that any point on the ground theoretically has a line of sight to at least 6 satellites at any time, as long as there isn't a skyscraper or a mountain in the way. Each GPS satellite continuously transmits messages indicating the exact time of transmission and the exact position of the satellite at the time of transmission. The GPS receiver in your car detects this signal, and using its own internal clock, it calculates the time that was required for the signal to travel from the satellite to the receiver. Because electromagnetic waves propagate at the speed of light, this time measurement must be extremely precise. Yet no matter how precise it might be, this measurement can never be perfectly accurate because the clock in your GPS receiver can never be perfectly synchronized with the clock in the satellite. The inevitable difference between satellite time and receiver time is called clock bias. No doubt you remember from your high school physics that distance equals rate times time. So once the transmission time is known, it can be multiplied by the speed of light, the rate at which radio waves are transmitted, to determine the associated distance from the satellite to the receiver. This distance is related mathematically to the positions of the satellite and receiver by this equation, which is really just the Pythagorean theorem extended into 3 dimensions. In this equation, x, y, and z represent the unknown position of the receiver in 3-dimensional space. X sub I, y sub I, and z sub I represent the known position of the satellite, and d is the distance between the satellite and the receiver. But d isn't really a known quantity because it includes the uncertainty associated with the unknown clock bias. So we need to rewrite this distance as the elapsed time plus the unknown clock bias multiplied by the speed of light. Called the navigation equation, this expression has 4 unknowns, x, y, z, and the clock bias, which I've called b in this equation. Thus, by the rules of algebra, this equation does not have a unique solution. But if the GPS receiver acquires independent position and time data from 4 satellites, we can write 4 such independent equations, and the resulting system of 4 equations in 4 unknowns can be solved. And this is precisely what your GPS device does. The receiver in your car is constantly listening for the position time messages transmitted by that ever-changing swarm of satellites overhead. At regular intervals, it resolves the system of 4 navigation equations to determine your position in 3-dimensional space. And then it displays this position superimposed over a digital map that's stored locally in the device. The device's other functions, determining a route, calculating the distance to your next turn, and speaking to you in that annoying voice, are also performed locally by the device's internal processor with no further interaction with the satellites. But of course, it's the satellites that make this amazing system possible. During this lecture, we've seen how our daily lives are influenced by highly sophisticated technological systems operating thousands of miles above the Earth. In the next lecture, we'll spend some time at the extreme opposite end of this technological spectrum, as we explore a potpourri of common household gadgets and gizmos reflecting engineering applications that, if not quite as sophisticated as communication satellites, can be just as fascinating.